the same. Okay, our aluminum is still the same. Okay, so 2468 box 2468 squares. Okay, now the steel has to be 2.86 times. So the steel is, it looks like this. Okay, so the steel will look like this. Okay, I'm going to draw this like this. Hold on. Then the steel part, so the steel is what? So the steel will look like this. So now we replace the steel part with what? Aluminum. Okay, for analysis. So over here, this is, we replace this with steel. Okay, this we replace with aluminum. Okay, because steel being stronger, right? When the top part is replaced with steel, you need to put in what? More aluminum. Okay, and it's all because why we analyze it this way is all because of the second moment of area. Okay, or not, this itself just get very muggy and complex, and it's not right. Okay, that's why we fix our what? We fix our depth and held our width. Sorry, we fixed our depth and vary our width. Now, so now if we were to go back to analyze a structure, right? And this is due to bending. Okay, this is due to bending. I'm going to write up the analysis. Okay, when we do sandwich or composite material under axial loading. Okay, how does the equation look like? Okay, so before I go on, so we know that the equation. So let's say we want to find stress X of steel. This will become N of steel. Okay, mz over izz multiplied by y. And we want to find the stress X of aluminum. This will become A of aluminum multiplied by mz over izz multiplied by y. Okay, so now, what if now we change, we look at axial loading? Okay, so let's now consider axial loading. Why we have to consider axial loading? Because later on we're going to do an example on eccentric symmetrical bending. So you have to have the term under the axial load. Okay, so now let's consider sandwich material. Or composite material under axial loading. Okay, so let's say if we have a material over here, there's a sandwich material. Okay, so now this is, we look at, this is not the cross-sectional view anymore. Okay, so this is X, and this is Y, and this is rotation about Z. And then we have one layer of material over here. Okay, so you have material number 1, and then we have material number 2. Okay, so you have material 1 and 2. And then if we have an applied load, P, X, and we also have applied load over here, which is our P, X prime. what will happen now is the structure will stretch. Okay, the structure will stretch. Okay, so I'm going to draw in red. The structure will stretch in this geometry now. Okay, the structure will stretch, and then originally here to here, this is our L naught, and then now because of the stretch, we have a length over here, which is known as L1. So the distance from here to here is our delta L. Okay. So what we are going to do is we know, right, material 1 will go through a load, right, over here on material 1. I'm going to call P1, and on material 2 will be P2. Okay, so we can almost immediately write down Px prime is equal to P1 plus by what? P2. Okay, and then we're going to assume that the strain induced, okay, the strain induced on both materials are the same. Okay, and why is that? Okay, why we assume that? This is because because the strain induced is generally small. Okay, the strain is small. So strain of material 1, okay, we're going to assume to be equal to the strain of material 2, and this is equal to L1 minus L naught over L naught. So we will have delta L over L naught. Okay, so this is equation number 1. And as I said, right, the strain induced is small. And why I mentioned that is because based on Hooke's law, remember all these are in the what? Elastic region. So based on Hooke's law, okay, based on Hooke's law, the stress and strain has a linear relationship and, okay, the strain induced is small. Okay, so from here we can write Hooke's law. Okay, so stress 1 of material 1 is equal to E of material 1 strain of material 1. So strain of material 1 is equal to stress 1 over E1. Okay, and then we also can write stress of material 2 is equal to stress 2, Young's modulus of 2, strain 2. Strain 2 is equal to stress 2 over E2. Okay, So from here, we know, right? We come out an expression. Note, we came out with an expression that we have px prime is equal to p1 plus by p2. Okay, we came up with that expression before. All right. So we know that px1, right, is equal to stress at material 1 A1 plus stress of material 2 A2. Okay, so if we come back to here, over here, right, this is A1, area surface 1, and this is our A2. Okay, so we know, right, we know this expression. Okay, so we also can also write out that strain of 1 is equal to strain of 2, right? We assume from equation 1. So from equation 1, right, strain of 1 is equal to strain of 2. So this expression over here, equation number 2 over here, can also be written as stress 1 over E1 is equal to stress 2 over E2. Okay, we can write that out. Okay, so if when we have that in mind, right, we also can write px1 is equal to px1 is equal to stress 1 on px1 is equal to uh stress 2, right, E1 over E2 A1, okay, plus by stress 2 A2. So what happened down here is what I've done is over here, if I put a comma, right, we can write stress 1 is equal to E1 over E2 multiplied by stress 2. You see that? So I substitute this into this expression over here, right? I get equation number 3. Okay. So from here, we can find stress 2. So we just bring up stress 2. So px prime, so stress 2 or stress, normal stress in material 2 is equal to E1 over E2 multiplied by A1 plus by A2. So therefore, stress 2 is equal to Px prime over E1 over E2 multiplied by A1 plus by A2. Give me, I know I went over, give me 1 more minute, okay? So that is material, normal stress for material 2. Normal stress for material 1 is equal to Px prime over A1 plus by E2 over E1 A1. Okay, so what you can see, the sandwich material for axial loading, the equation is not so straightforward. It's a bit more, not a bit more complicated, but there are more steps to deriving it than what we had before. Okay, what I propose is we go for 5 minutes break. We come back at 8:20. Okay.